Swayamprabha. Digital India. Educated India.
Welcome you all again to this course on CFD. We are now on to module 3 of week 2. So far we have done definition of computational domain, structured grid, unstructured grid, and how to obtain difference formula from Taylor series expansion. In today's class, we will take this to the next level of obtaining finite difference scheme for first as well as second derivative, and then how to obtain higher order accurate scheme again by all the three methods for both first as well as second derivative. After that, we will move on to the remaining syllabus content in the subsequent modules. So, towards end of last class, we have derived forward difference scheme from Taylor series expansion, and by using I notation form, we wrote expression for first derivative as dou f by dou x at I f of I plus 1 minus f of I by delta x, and graphically it is shown here f on y axis, x on x axis, and dou f by dou x is evaluated at point B for the function that is represented here. And we also wrote down the final formula for the same first derivative by using backward differentiation scheme, and that is shown here as dou f by dou x at I equal to f of I minus f of I minus 1 by delta x. We also noticed that this is of order delta x, which is a leading term that we have not considered. It is also to be noted the derivative error associated with the derivative gets reduced as the delta x is reduced. Now, in today's class, we will see detailed steps on how to obtain this backward differentiation scheme formula. So, as we did for forward differentiation scheme, we write down Taylor series expansion for the function f of x in backward direction as f of x minus delta x equal to f of x minus delta x into dou f by dou x plus all other higher order terms. And you have to notice that this is alternate sign with the delta x first term, then third term, and so on. As we did in the case of forward differentiation scheme, one can also write the entire expression in this format with summation sign going from n is equal to 1 to infinity and minus delta x to the power of n by n factorial and all other higher order terms. So, we are interested only in the first derivative. So, we take only the first term dou f by dou x, and remaining terms are not considered, and so this delta x is taken to the other side. Then we are able to write in I form dou f by dou x evaluated at I as f of I minus f of I minus 1 by delta x, and this is also of the order delta x. So, the next is we had forward differential scheme, backward differential scheme. There is also what is known as a central differential scheme. So, in forward differential scheme we had expression For example, for dou f by dou x at b is related to values of the function at b and c, and in the case of backward differential scheme it is related to the value of the function at b and a. Now, in central differential scheme it is related between a and c. Now, we will see the steps. So, we again write down expression for Taylor series expansion f of x plus delta x like this, and f of x minus delta x as shown here in equation 4, and these two are familiar. Now, we have to do again a small arithmetic operation, and we observe here dou f by dou x, another dou f by dou x from equation 3 and 4 respectively. So, if you subtract equation 4 from equation 3, so this is equation 4, which is a backward difference backward expansion formula, and this is expansion in the forward direction. So, if you subtract equation 4 from equation 3, you can get f of x plus delta x minus f of x minus delta x. The first term gets cancelled, second term it becomes positive. So, 2 times delta x dou f by dou x plus all other higher order terms. Again we are only interested in the first derivative here. So, we retain the first derivative and take remaining terms to the other side. So, if you write down dou f by dou x f of x plus delta x minus f of x minus delta x by 2 delta x, and here it is delta x to the power of 3, and this delta x here when it is divided here the power gets reduced by 1. So, it is of the order delta x squared. In I form it is written here dou f by dou x equal to f of I plus 1 minus f of I minus 1 by 2 delta x and order of delta x squared. Now, we will also see how to write down difference formula for higher derivative. We have seen so far f of x plus delta x. Now, we can also do the expansion for any length of delta x. So, what is shown here is for 2 delta x. So, f of x plus 2 delta x, the formula is almost the same except that delta x is now replaced with 2 delta x. So, if you subtract equation 5 from equation 6, because we are interested in the second derivative dou squared f by dou x squared, and we need to have other terms cancel. So, we do operation subtracting equation 5 from 2 times equation 6. So, we get f of x plus 2 delta x minus 2 times f of x plus delta x, then some of the term will get cancelled. Now, you see here only the second derivative term, that is dou squared f by dou x squared. We are again interested only in the second derivative. So, we retain that on one side and bring all other terms to the other side. Again we have written here up to the next term only, all other terms are not written here. So, if you bring delta x squared from one side to the other side, this delta x cube will get reduced to only delta x. If you do that way, then we get f of x plus 2 delta x minus 2 f of minus 2 f of x plus delta x plus f of x by del x squared and of order delta x for the second derivative dou squared f by dou x squared. And in I form it is written here f of I plus 2 minus 2 f of I plus 1 plus f of I by del x squared and again of order delta x. Now, this is getting the second derivative in the forward direction, that is I plus 2 and I plus 1 function values at these two locations are used. Just like we did for forward differencing in the case of first derivative, here also we have expression evaluated based on function values in I plus 2 and I plus 1. Similarly, you can also get expression in backward difference form following the same procedure, and what is shown here is a final form, which is f of I minus 2 f of I minus 1 plus f of I minus 2 by del x squared for the same second derivative, again with the order delta x. You can also obtain central differential scheme for the same second derivative. So, again we write down Taylor series expansion in forward direction as well as in backward direction, and we do the arithmetic operation, add equation 3 and equation 4. So, we get f of x and here f of x square 2 times, and we want only the second derivative. So, after doing this operation, then we get dou squared f by dou x squared at f of x plus delta x minus 2 times f of x plus f of x minus delta x by del x squared, again of the order of del x squared. So, you can observe the function value at that point of interest and function value on either side. So, which is x plus delta x on the forward direction and x minus delta x on the backward direction. These values are used. So, it is called central differential scheme, and this is evaluated for second derivative. And you can also write in I form, that is what is given here as f of I plus 1 minus 2 times f of I plus f of I minus 1 by del x squared of order del x squared. So, if you put all the 3 terms together in graphical form to get an idea of how these are evaluated. So, what is shown here is function on the y axis, that is f, and on the x axis you have x marked. I is a point of interest, I plus 1 and I minus 1 are immediate neighbor on the right side and left side, and you see a curve here, that is actually the function, and you are evaluating slope of the function. So, when you say derivative forward, when you say first derivative, you are actually evaluating slope of the function. So, dou f by dou x is evaluated at the point of interest at I. So, by following forward difference formula, which is written here again, f of I plus 1 minus f of I by delta x, it is evaluated, the first derivative slope is evaluated by considering function values at I and I plus 1. For backward differencing, it is evaluated using the function values at I and I minus 1, and for central differential scheme, it is evaluated using function values at I plus 1 and I minus 1. So, you see here the function curve actually is this way, and you are evaluating slope by 3 different methods, and for each method there is an error associated, it is not always perfect. And we can also observe as you decrease the delta x, that is the distance between 2 subsequent grid points, in this case it is I and I plus 1 or I and I minus 1, one can get a slightly error reduced value for the same slope. Now, we also have higher order FD, in the sense we have seen first derivative evaluated by Taylor series formula with order of accuracy of delta x. We observe that you can reduce the error by reducing the grid spacing, but that is not always possible. We have a limitation in having number of grid points or other practical difficulties to have a finer grid. So, is there a way to get higher order without increasing the mesh size? It is possible by considering additional terms in the Taylor series expansion, and that is what we are going to see, that is known as getting a higher order finite differential scheme again for any derivative, first derivative, second derivative or any other derivative. So, in this case we write down here the first derivative formula dou f by dou x in forward difference method. So, f of x plus delta x minus f of x by delta x and remaining term, and you can observe that dou squared f by dou x squared is an immediate term previously we did not consider. Now, if we know that we also got expression for the second derivative again by all the three schemes, that is forward difference, backward difference and central difference scheme. So, if we can replace this second derivative appropriately, then follow some simplification, we will be able to get higher order finite difference scheme for the same first derivative, and we are going to see that. So, in the case of first term when we did, we considered only the two terms. Now, to get higher order we will consider one more term. So, you substitute, because we are interested here forward difference. So, you substitute for this second derivative in terms of forward difference, and that we already obtained the previous steps, that is given here once again, which is given as f of x plus 2 delta x minus 2 f x plus delta x plus f of x by del x squared of order delta x. So, if you substitute this expression for the second derivative in this equation and then simplify, you just try to account for all the terms together, reorganize, then one can get forward difference approximation for the first derivative, and that is shown here, dou f by dou x as minus f of x plus 2 delta x plus 4 f x plus delta x minus 3 times f of x by 2 times delta x, and here the leading term that we have not considered is here. After dividing delta x, you find this is delta x squared, the term that is not considered becomes order. So, order of delta x squared, and if you compare what expression we got the first step, that is considering only the first term. So, that we have f of x plus delta x minus f of x by delta x, and that is of order delta x for the same first derivative. So, by if you observe these two expression very closely, here we consider immediate neighbor, that is x plus delta x, and in the higher order expression we consider immediate neighbor x plus delta x and one more immediate neighbor which is x plus 2 delta x. So, you can get an idea that by considering more number of nodal points, function values at more number of nodal points, you are able to increase the order of accuracy, and in this case as you can observe of order delta x to of order delta x squared. Once again, this is not a permanent solution or a solution for all situation, that is you can get higher accuracy by considering more nodal points. There is always a limitation when it comes to applying. For example, if you are in a computational domain, if you are on the right side of the boundary, then you have a very limited choice of considering more points beyond the boundary limit to consider forward difference scheme to get a derivative by forward difference scheme. So, you are limited by number of grid points available beyond boundary location. So, either it is the forward or backward, there is always a limitation. Now, so just like we obtain higher order finite difference scheme by a forward difference procedure, we can also obtain higher order finite difference scheme by backward difference procedure. So, what is shown here is backward differencing formula for the first derivative. This was already obtained, and we follow the same procedure, that is the second derivative, that is the next term that we have to consider, replace that second derivative term by backward differentiation formula that we obtained, and that is shown here as f of x minus 2 delta x minus 2 f x minus delta x plus f of x by del x squared, and this is of order by independently this is of order delta x. Now, we replace the second derivative term by this backward differentiation formula for that term, and again properly reorganize with the corresponding terms, and we end up getting backward differentiation formula higher order finite differential scheme for the first derivative dou f by dou x, and you can again observe that this is rearranged and we get finally a formula like this. And as we observed in the case of forward differential scheme, f of x minus delta x is an immediate neighbor point in the backward direction, and x minus 2 delta x is one more additional point in the backward direction. Now, if you compare this formula with lesser accuracy, that is the first order accurate, then you get formula here. So, only 2 points are considered and you have additional point considered, and that results in slightly a next order, that is order second order accuracy. So, as I mentioned in the forward differential scheme, it is not always possible to implement, though it appears a solution to get a higher order accuracy. So, earlier we have seen by decreasing delta x you can slightly get higher accurate approximation. Alternatively, as shown here, by considering more points you can get higher order approximation for the same first derivative. Now, the last few slides we have seen how to obtain higher order finite differential scheme by both forward differentiating as well as backward differentiating for the first derivative. We will now extend this procedure to get higher order finite differential scheme for the second derivative, for example by central differentiating procedure. What is shown here is a final obtained formula, and as you can observe here, this is of order 4, and if you compare this with the original expression that we obtained by second order accurate scheme, you observe that second order accurate scheme has point of interest and one node on the left and one node on the right. To get fourth order accurate scheme, we have in addition 2 more nodes, one more extra on the left and one more extra on the right. So, by considering additional points, one is able to obtain higher order. It is also possible to do similar exercise for higher derivative scheme. Now, with this we come to end of this class. We will take another interesting part in the next class. Thank you.